So, hello everyone. I'm presenting our NURIPS paper on supervised meta-learning for few-shot image classification. The authors are Siavash Khodadade, Ladislav Bloni, and Mubarak Shah. So the outline of my talk would be, I will talk a little bit about the background, few-shot learning, what few-shot learning is, a little bit about meta-learning, and one particular type of meta-learning, model-agnostic meta-learning, and then I will talk about our paper on supervised meta-learning and the experiments and results we get. So what's few-shot learning? So humans learn very quickly and from few examples. So if I show you two different characters and I ask you which one is this, you can easily say it's the first one and this is the second one, even though there are variations in these drawings. And that's because we know a lot of things about handwritten and handwriting, and you can easily recognize this is none of them. So the question is, can machines do the same thing? So in order to answer that question, we first need to formalize our problem. So we need to have a formal definition for our problem. So we define a few-shot learning task tau, n-way k-shot. So we want to n-way classification with k-shot. So when we have a training data for that task, which has pairs of x and y, and it has n classes, and for each class we have just k samples. So we call that an n-way k-shot task. And also it has a validation data, which also again is also from these n classes and has k samples for each of those classes. For example, if I want to show you a three-way one-shot task, this is a three-way one-shot task. So there are three different classes: archery, long jump, diving, and three different actions, and we just have one example for each action. And that's the trained set of that task. And it also has a validation set. So validation set has different instances of the same classes. And of course, if you want to evaluate it, you can evaluate it on more examples in validation. But the thing is that in your trained set, you just have one instance each, because this is a one-shot task. So I will talk about model-agnostic meta-learning. So the intuition is that we want to learn representations which are transferable among tasks. And those representations should give us large improvement on loss function of any particular task when we start from that representation. So as I showed you before, a task is like this. So it has a train and a validation set. So this is another example of another task. So there are three other classes: horse race, swing, playing violin, and it has its train and validation set. So you can imagine that I have lots of tasks like this. I can generate as many tasks as I want, and I put all of them in a set and call them meta-learning tasks. So these are all the tasks which we use for meta-learning. And then after we are done with the meta-learning part, we have a target task. So a target task is again the same thing. It has three different classes, like walking with dog, psycho penalty, juggling, and it has its own train. And you have just one example of each classes, and you want to learn that task. That's the task which is your target, and you want to learn it. So you evaluate it on the validation. And again, we can have as many target tasks, a lot of different target tasks. So we can put them also in another set, and we call them test tasks. And the important thing is that the classes are not shared. So you have never seen walking with dog during the tasks in meta-learning. So that's completely a new class that you have to learn. So you want to learn that task, you have never seen those classes before. So what we learn when we do meta-learning on that meta-learning task set? So the answer is actually simple. We just learn the initial weights. It might seem simple at first, but the intuition is like transfer learning. So when you do transfer learning, you start from a good initial point. So we want to learn that good initial point. So if I want to give you some intuition, so we have our parameter theta, and we want to learn three different tasks. So I call them theta, task 1, task 2, task 3. And let's assume that theta star is the best parameter values for that task. So we want to learn those tasks. So if I perform one step of gradient descent with respect to the loss function of the first task, I will go to here. I will go to here from theta. And the same thing is true for the second and third task. But during meta-learning, I will learn to update the theta parameter, and then I will end up here after meta-learning. So now if I want to learn each of those tasks, I can easily learn the best parameters for that task. So that's the intuition. We want to learn this good starting point from which we can learn every task quickly. So our method, the method in meta-learning, if we want to learn the task Ti, so we start from our model parameter theta, and then we update our parameter based on the loss function of that task, which is loss function of Ti for that task, and we perform gradient descent starting from theta. So that would be the parameters for that particular task. So for any task, you can assume that you can just apply gradient descent and you get the parameter for that task. So our objective is to minimize this loss function of the parameters when we adapt to those tasks. So when I update my parameters to the theta prime I update my parameters to that particular task. And then I want the loss function on that task to be minimized. So actually what we want to minimize is this. When I update my parameter starting from theta, I update my parameter to the parameters for that particular task. I want the loss of that task to be minimized. So that's what we're minimizing during the meta-learning. Yeah, and we can also extend this by more steps of gradient descent. There is no rule to just apply one step. You can apply as many steps as you want. So this is the algorithm for meta-learning, supervised meta-learning. So we have a distribution of tasks, and we have two hyperparameters, alpha and beta, which are the steps which we pick. The alpha is for the task and beta is for meta-learning. So we randomly initialize our parameters, and we repeatedly sample a batch of tasks. So we pick some tasks from our meta-learning task, and for each task we look at the trained data set, and we look, okay, if I want to learn this data set, how should I update my parameters? So this is actually the signal which tells you how should you update the parameters. And this is the parameter which you get after you update your parameter based on the loss function of that particular task. So you have the updated parameter for each task, and you also look at the validation of each task, validation set of each task. So you also look at the validation set of each task. And then you update your theta parameters to give you the theta parameter to give you the so you perform one gradient step based on the validation loss you get from these points. So you update your parameter based on the for this task, and then you evaluate it on the validation, and then you want this validation loss to be minimized. So you apply backpropagation through that. So I also visualize one step of meta-learning, one iteration on one task. So let's see how it works. So for example, let's say that we have a data set which has 1,200 different classes. So I just want to apply one step of meta-learning. So what I do is that I sample n different classes. So I just randomly pick n different classes, and then I pick one example from each class and put them in train set. That would be my train set. And I know the classes of those, and also I pick another example of each class, another example of each of those class, and I generate my validation set. So I look at each class and I pick one for train and one for validation set of that task. So actually I sample 2 data points from each class, and then I apply my meta-learning algorithm. So it actually works well. So this is MAML paper. They have done it on OmniGloat. So OmniGloat is a few-shot learning benchmark, and it has 1623 characters from 50 different alphabets, and each character has 20 instances, each drawn by a different person. And it's splitted in 1,200 characters for meta-learning and 323 characters used for tests. And as I showed you, we can generate different target tasks. So we generate 600 different target tasks, and we average the result on those when we want to evaluate our method. And Yeah, so this is the mammal algorithm, and you can see that they have done it on 5-way and 1-shot and 5-shot. So 1-shot is when you just train on one example, on one character, and you want to evaluate it on other characters of the same class. So it gives actually very good results, and also for 5-shot and also for 20-way. Here we have 20 different classes for each task. So that would be OmniGlout, and also for Mini ImageNet. Mini ImageNet is also another well-known benchmark for few-shot learning. So it has 80 training classes. We use 64 training classes for train and 20 used for test, and 16 are for validation. And every class in Mini ImageNet has 600 different examples. So in OmniGlout we had 20 different samples for each class, but here we have 600 different samples. And we again generate 600 tasks for test. And as you can see, the images here are more complicated than in OmniGloat. So they also applied their method on Mini ImageNet. So here we have 5-way accuracy on 1-shot and 5-shot. And you can see that mammal works very well on these data sets. So we wanted to see if we can apply this on other domains. So we considered 2 other domains, face recognition, which has so we applied it on a data set of faces, Celeb A, which is a well-known face data set. And we also wanted to evaluate this on human action recognition from videos, and which is a much more challenging domain, and we used UCF 101 here. So on Celeb A, again, we have the same definition of task. These are the faces of celebrities, so we sample different celebrities and we put them in train and validation. So it's a larger scale face data set, and each subject has different number of images, so it's an unbalanced data set. And it's not like OmniGloat in that you have 20 instances for each class. Each class might have different number of examples. And we use the same train validation test division as suggested. And we test on 1,000 different target tasks. So we do meta-learning and we test it on 1,000 different tasks. So we compare with training from scratch. So training from scratch means that you do not do any meta-learning. You just start from initial random weights. And you can see that supervised meta-learning gives very good performance on this data set. So for action recognition, we wanted to evaluate meta-learning. Again, there are no few-shot learning benchmark on videos. So we shuffle all the actions on UCF 101, and at each step we pick 5 actions, and we just pick one sample from those actions, and we train our network based on just one sample of those actions, and then we evaluate on all other examples of that class. And then we do this for 30 different tasks, and we average the results. So the model which we use is C3D model, pre-trained on sports 1 million. And the data set which we use for meta-learning or transfer learning, we use kinetics. So we applied transfer learning and also meta-learning to compare them together. So here is what we do for evaluation. So we have one target task, we look at the train set, we adapt our network to that, and then we evaluate on all of the samples of the test for those 5 classes. And then we go to the next task, which is, and we do this for 30 different tasks. And these are our results. So we report accuracy and F1 score. So if you train from scratch with just one sample from each class, this is what you get. And this is pre-trained on kinetics, and this is supervised meta-learning on kinetics, the results which you get if you do supervised learning. So until this point I was talking about supervised meta-learning, but our paper is about unsupervised meta-learning. So we wanted to see if we can do the meta-learning part in an unsupervised way. So the idea is, again, there is an intuition behind this. So if you look at human, most of the time we do unsupervised learning. We do not get supervision. So, and we just get few samples for supervised learning. For example, when a child plays with a toy, you just go and tell them that this is purple. That's just one supervision signal, but they have spent a lot of time looking at that toy and playing with it, so they have learned a lot of things about it in an unsupervised way. So we want to see if we can do that meta-learning part in an unsupervised way, and then do, so we want to see if we can generate the tasks in an unsupervised manner. So we call our algorithm unsupervised meta-learning with tasks constructed by random sampling and augmentation, UMTRA. And the goal is to do unsupervised meta-learning. So we have a data set which is not labeled, and now we want to do meta-learning on that. So we just sample n data points from that data set. We do not know their classes, but statistically, actually, we show in our paper that the probability that they are being from the same class is not that much. So we can assume that belong to different classes. So I can create a train set based on this. So I put them in different classes, and I do not know their labels. So we just give them artificial labels, 1 to n. And then we want to generate our validation set. Okay, if we want to sample again from this data set, we probably end up with other examples of other classes. We cannot get other instances of these classes. So we actually come up with a simple idea which actually works very well, and that's just to do augmentation on the same points which we sampled previously and generate our validation for that task in that way. So we use the same point for train and validation, but we apply augmentation for the validation. And then we do the meta-learning algorithm. So that's just how we construct tasks. So this is our algorithm. So we have n-way classification. We have a meta batch size, and we have different number of updates. And we have an unlabeled data set. And again, we have a step size hyperparameters, and then we have our augmentation function. So here we need to do augmentation, so we need to have a function for that. Again, we randomly initialize theta, and we repeatedly, for each batch of tasks, we just sample n data points from our data set, and we generate that task's trained data set. And then for each task, we generate trained data set by giving those samples artificial labels, and then we start from theta prime I. So that would be the parameters which we want to learn for this particular task. So at first we initialize it with theta, and then we have nu number of updates. So we repeatedly just evaluate the loss based on the theta prime I, and this is just nu steps of gradient descent. And we compute theta prime I at each step. And then we generate our validation set. So our validation set would be the augmentation function applied on those data points, and also the same artificial labels which we used for them. And we update our theta parameters based on this.
You want to say you sum up, right? That you sum up these.
Yeah, because this is a meta batch of tasks, so we look at the loss of all of those tasks, and then we sum up over all of those tasks. Yeah, that's actually important. So, yeah, so that's our algorithm. And let's go into the results. So we evaluate our results on OmniGloat, Mini-ImageNet, Celeb-A, and UCF101. So for OmniGloat augmentation, we use translation and pixel dropping. So if we have this data for a task, this would be what we do. So this is the augmentation which we apply for OmniGloat. Another choice of augmentation is auto-augment. Auto-augment is actually a paper, auto-augment learning augmentation policies from data, from Google Brain and by Kubek et al. And the idea is to learn policy for augmentation by reinforcement learning. So we use reinforcement learning. We have an action. The action is a sequence of augmentation operations. So this consists of 3 hyperparameters each action. The operation type, which could be translate, shear, rotate, auto-contrast. So it has 16 different choices for operation type. The probability of applying that augmentation, and also the magnitude. How much should I rotate the image if I apply rotation or something. And then the reward is the accuracy on a validation set. So we do those augmentations, we evaluate on a validation set, and that would be the reward. So that's how we learn how to augment data sets. So for ImageNet augmentation, Mini-ImageNet augmentation, we can use the same augmentation function, flip the image, or use grayscale, rotate, or a combination of these, or we can use auto-augment. So it's just auto-augment policy to apply augmentation on the images. So we evaluate our method on few-shot learning benchmarks. So here is our method OMTRA. And these are like different clustering algorithms, and then we apply a classifier on top of those clusterings based on just few examples we have. And so we evaluate on OmniGloat for 5-way one-shot, 5-way 5-shot, 20-way one-shot, and 20-way 5-shot. And you can see that Omtra actually works pretty well on this data set, and it's very, very close to supervised learning algorithms. We also evaluate on mini-ImageNet, and we get very good results on mini-ImageNet as well. We are comparable with the state-of-the-art, and you can see that it still is able to learn when you increase the number of samples. So we also do some ablation studies on OmniGloat. So we wanted to see the effect of the augmentation function to see how it affects the results. So if we just use the same augmentation function, it means that you use the same train set as validation set. So that's not a good idea. And you can see it doesn't give you that much improvement. But you can use different augmentations, and it shows that when you use good augmentations, you can actually get very good results. We also wanted to see the effect of translation of the images on the result. So if you just translate images by 3 pixels, or by some random numbers between 3 or 6 pixels, or between 6 and 9, and we can see that augmentation works fine to some level, but if you want to just do a lot of augmentation which completely loses the information, then it's not going to work. And we also do ablation studies on mini-ImageNet. So it's again something similar. So we apply different augmentation function and we look at the results. And here auto-augment actually gave us very good results because it applies good augmentation on the images we have. So we also evaluated our method on celeb A. So here is how we generate tasks for celeb A when we use supervised mammal algorithm. And we also again use auto-augment on celeb A. So you can see we just augment those images for each task. We flip or do different augmentations, and we use them for train and validation. So yeah, and this is the result which we get. And we still get very better results than in comparison with training from scratch. And this is the supervised technique. And okay, and also video domains. So we want to do video augmentation, but we have a good choice for videos because video are clips, so we can pick 2 different parts of the same video clip, and we use one of them for train and the other for validation. So for example, this is a video of a person giving a talk, and you can just sample 2 different parts of this video clip and use that, use one for train and the other for validation. Or like playing cards, or I guess this one is uploading or something. So you can see that this gives good augmentation to us. So we evaluate again on UCF 101. If we train from scratch, this is what we get, and if we use pre-trained on kinetics, this is what we get. And this is Omtra on unlabeled kinetics, which gives a very good result. And this is supervised mammal. And one final ablation study which we did was to visualize the features which we learn by meta-learning by t-SNE. So t-SNE is a method which plots high-dimensional data in a 2D space. And we want the features extracted by network should be similar if they are in similar classes, and they should be separable if they are from different classes. And so we use t-SNE to visualize data. So actually what we visualize is the last hidden layer of the network, so we can call them the features, the last hidden layer vector. And so this is when we just do training from scratch, so no meta-learning. So this is one task of OmniGloat. So we have 5 different characters. Each character has 20 different samples. And we have 5 different classes. And we just use one example for each class to train our network. And then we train our network. We apply t-SNE on the feature visualization for all of the samples of that class. So this is what we get. So these are which are connected to each other with dotted lines. They are just the ones which we used for training. So for example, after we do the training on this task, Okay, so this is the feature space, so we want it to be linearly separable, or we want to be able to apply, for example, think of it if you want to apply KNN on it. So this is the point which we used for training, but you can see the other examples of this class end up in somewhere which is not close to this one. So because we just trained from scratch, we just saw those examples. Yeah. But for Amtra, again we do the same thing, the same task, but this time we start from the parameters which we learned by Amtra. So here is what we get. So as you can see here, the instances of the same class end up so much closer, even though the network has not seen them. It just has seen one example, the same example from each class. But the feature space will be much better here. So we propose an unsupervised meta-learning algorithm which is based on generating synthetic tasks. And we show the relationship between validation and train set and augmentation. And also we evaluate our result on different domains, few-shot learning benchmarks, videos, and face recognition. So that's it. Thank you.